and welcome to this week's Great Egg Race. We've once again invited 3 teams of 3 people to tackle a relatively simple problem, and the teams will, as usual, have only a limited time for their discussions and construction work. Well, let's meet this week's contestants. Behind me from Contron Electrolab, we have David Tompkins, who's a mechanical engineer, Ed Bayliss, a chemist, and Brian Rook, an electronics engineer. Our second team comes from DIS in Norfolk, and they're all research biologists from Life Science Research. Peter McAnulty, Chris Willoughby, and Owen Wilby. And our third team are all computer scientists. They're from International Computers Limited in Bracknell, Berkshire. Keith Shepherd, Doug Urquhart, and Ian Fowler. Our specialist judge this week is Professor Gordon Higginson, and our resident judge, Heinz Wolf.
At one time or another, we must all have tried to win nearly unattainable prizes at a fair by throwing a hoop over them. Well, today's problem is really rather like that, except, of course, that the rewards of winning are infinitely greater. What the teams will have to do is to make a hoop projector. We should project these 18 hoops in 90 seconds at a range of 4 meters over these 3 pegs. But a hoop will only win marks if it lands on a peg of its own colors. Hooplistics, I call it. I wonder what the teams will call it.
Yeah. Device start line.
Basically. On variable heights, notice.
Yes, yes.
They got a spin to go.
A set of hoops over the peg of a similar colour. Okay.
Just out of curiosity, how far is 4 meters? I mean, that's the middle.
Well, fairly far. I mean, it's about as far as from there to... it's about as far as the distance across here.
Yeah.
That's all.
That's not very far, in the big hoops.
That's right, that's right.
Hoops are going to run flat, so we can't have this back edge killing all the energy. What I'm saying is, instead of the hoop going like that, you've got to go like that. Yeah. So this goes... Yes?
Yeah. That's really
then
if you do that, it's just going to do that. But if you have too much horizontal velocity, the thing sort of flips right over and flips off again.
So if we look at... The biggest thing is going to be able to adjust it finally. We've got to have adjustment on the amount of energy we put into it, adjustment on the actual angle of the hoop when launched, and the actual angle of takeoff.
Well, look, if we have something along these lines, where the... Yes, is it possible, perhaps, that we can work out something which performs an arc like that? With the resultant peg there, a flip over. Flat. Okay, assuming we have...
A catapult, you mean?
A catapult, but a flat catapult. Let's call it a flatapult. If we have a box, for some variety, with a sprung doings there, okay, some form of doodah to hold the wretched thing down, and we can lay the hoop on top.
Yes, you mean something?
Yes.
Drop something.
Yeah, that makes
hinge, spring.
That makes letting go very easy, doesn't it? I mean, otherwise, any sort of thing.
Maybe we need to put a stopper for it to stop.
Yes. No, we don't actually want a hinge here because we want enough upwards movement here to stop the thing just flipping over and landing there, don't we? So basically we want
a longer arm on it.
Well, I think with a bit of testing, it's this height here that we need to vary. As to how much, you may just get to go just like that.
Yes.
And stop.
Yes. Okay. Well, varying the height can be done by just varying the length of the legs underneath. That's no great problem.
As soon as it hits that stop, it's going to carry on going, and because that was there, it's going to impart that spin to it as it goes.
Well, once we've got it out and spinning, then we've got to think about how to get it over various heights.
Yeah.
And I think that could be simple, either angling or angling the frame that it's on.
Because
raising it off the bottom.
We do each one in turn, don't we? So it's not a case of having to keep modifying it. Sort of going there. We do those, how many is it? Can't remember.
6 in each.
6. So we do 6 onto that one, 6 onto that one, 6 onto that one.
So, shall we do our action plan? One test. And we've got A there, we've got energy, and possibly B, the spin or angle. because that's the other way we can kill the energy, but it means that we don't have a big target area. If we look in that direction, compare with a peg, we've got that sort of area aiming for the peg. But if we're going flat, we've got a very small target area. So we've got to maximise that, I think.
I wonder how much chance we have to experiment to it.
Well, it depends how quickly you get, you get your prototype made, doesn't it?
Do we get a hoop to play with?
Oh, I hope so.
I would think we get a hoop or two. Good. We can always make our own hoops. Have a bit of piping.
There is a green pipe, but
Yeah.
no, that's
Yes, we
floppy.
do.
That wouldn't fly the same. But,
Yeah.
One each.
Not too heavy, are they?
Huh?
Not too heavy.
Yeah, they're fine.
No, give it a straightforward swing, okay? Yes, it does tend to rotate like that. That's good. That's good, provided, of course, it's going that way at the time it meets the meter stick.
hang on.
It may
it's
well
rotating
do.
this way,
Yeah.
right? And let's say the centre is somewhere around going to hit there. If we're accurate with the aiming, the height and length,
Yes.
then surely, unless it actually hits it bang on, it's always going to
It's
go over.
always going to go over, that's right, one way or another. Yes, yes.
When it's going really, really fast. Well, anyway. I mean, it's not going to, first thing, it's going to be coming down.
Yeah, yeah. Yeah,
Have to move it further down.
that's right, that's right.
Right,
Then you'll get the turning moment. Yeah.
Spinning around. Yeah, I suppose it's unlikely that I'd then do that.
Well, that's right, that's right. Actually, there is no reason why it should, because there's no force in that direction.
Can you actually?
Is there? Well, that's failure number one, anyway.
I mean, why?
Yeah.
Lower diameter.
Oh, that's a thought, yes, go on. Go on, then, give it a go. Failed, and again. Right. You've won a meter stick, sir.
Yeah.
Well done.
Gordon, we've created for ourselves an 8-to-1 scale model of the problem. Let's walk through this. The gun, whatever we have, rifle, catapult will be over here, distance of 4 meters to the middle and the highest peg, the 1 meter peg, but they've also be able to thread hoops over the smaller pegs, which are respectively nearer and further away.
Right.
Now, they have to impart a good deal of velocity to their hoop. What means do they have of getting this?
Well, there are a number of devices for holding energy that they can put into their gun manually. Perhaps the biggest or most powerful device is the bungee, this 6-strand elastic band that's used for holding the luggage down on roof racks on motor cars, for example. There's also a considerable energy capacity in the cycle inner tube, and then they have a number of much smaller devices, a variety of rubber bands of different sizes, and a not very attractive looking set of coil springs. I think they're quite unlikely to use these as the main launching power sources.
Now, they've also got a much more ancient form of storage of power, a piece of cane, really rather like a bow.
Yes, they can make a long bow with
and
that.
There's really plenty of urge in this. Now, am I right in thinking, Gordon, that one of the problems will be to accelerate the hoop over a considerable distance in order to give it enough energy? So you really want something which has some travel to it.
Yes, the length of their gun barrel, if we can use that as an analogy, does want to be fairly long because the velocity requirement is fairly high, I think. Perhaps a metre length, something of that sort. That's
Yes.
an equivalent to a quarter of the range.
But is it only a question of the length of the barrel, or do they want to continue to impart energy to the hoop for the whole length of this barrel if possible?
Oh, I think it's a much sounder internal ballistic arrangement if they can propel the thing over the whole length of the barrel.
So they really want something which has a lot of stretch.
A lot of stretch.
So the springs, as you said, were particularly unsuitable.
Oh, the little springs are quite unsuitable, and even to use the bungee, for example, they may have to use some mechanical lever arrangement to give them a magnification.
Now, in terms of the flight path, it clearly would be advantageous to have a flight where if any part of the back of the hoop intercepts a peg, it's captured.
Right.
So that really the cross-section of the hoop has to be made as large as possible.
Indeed, if they can orient the flight to be stable in that sort of orientation, they're practically home.
Right, well, let's have a look at what the teams were doing, what kind of solution they're actually going to adopt.
If you can skim it over the top of that.
Just hit the top. But it was, I think it was still going up at that point. Maybe.
Where are we losing energy?
Well, I think this is too high. I don't think we're going to go any higher than that for a start. You know, we're being dinged in on.
No.
Brian, could you give us a hand in a minute? What I want to achieve is get those hinges on there, but I think we best put the other rods on first. We've got to attach the main runners there, then we've got to bring two out there, and then we've got to have a carrier plate up the other end, which is going to be around the houses, possibly a wire hoop or whatever, just to support the top guides. Because we've got to stabilise the three ends. But that should be not such a problem. Our biggest problem is going to hold it together. Well, it's 19 inches. You see, if you see it in there, that should give us about a 45 degree...
These are the top two guides.
Yeah, that should give us about a 45 degree launch angle.
For tang. That's very surprising, actually. I wouldn't have thought there was enough... Demonstration, yes.
Well, the teams have now had 1 hour, and already the devices for firing hoops are beginning to take shape.
Quite. Right,
You seem to be building quite a solid structure. Is rigidity and things like that important?
well, we don't really know how much power we're going to have to use, and if it all falls apart at the last minute, it could be very embarrassing.
Yes. What power source are you going to be using?
We're going to use these thick rubber things.
Yes.
If they turn out to be too powerful, we'll go down to rubber bands, but I think these are probably going to be
Yes.
the sort of order of magnitude that we need.
Right. And can you explain what this is? I believe it's upside down at the
Yes,
moment,
if you think of it as a gun, this is the
Yes.
barrel, this flat piece.
Yes.
This is the hammer, and this is the
Yes.
motive power. So basically this hammer is going to hit the edge of a hoop, which is resting on the other surface of that.
So the hoop is sitting there doing nothing, and the
That's
hammer
right.
comes and
It'll
whams
clout
it.
the side, and hopefully
Yes.
it'll sail through the air gracefully and land over one of the pegs.
The right peg.
The right peg.
Well, let's not walk before we can run.
Yes.
Anyway.
Aiming going to be a problem?
Possibly. We haven't done enough experiments to tell, but hopefully these slabs along the side will give some measure of accuracy. We'll have arrangements for measuring the range, so when we calibrate it, we can get a rough idea of what angles will give us what range.
And then you can adjust accordingly.
We can adjust accordingly.
You hope.
Well,
Right.
that's right.
Thank you.
Okay.
David, can you explain to me quite how you're going to fire yours?
Well, we feel that the best angle to fire the hoop is to have it travelling at probably something like 45 degrees
Yes.
to its flight path.
Yes.
And to arrange that, we are intending to use 3 guides, which will hold it in an angular position like that.
Yes.
And then we will use a bungee to apply the acceleration force at the bottom of the hoop.
At the bottom.
And
sorry, carry on.
to adjust the range and height, we intend to have the launch guides moving in a conventional gun manner.
Yes. So that's attached at the bottom.
Yes.
It's taut to start with, and then it pulls the bottom towards it, but you've got a guide here that stops it just flipping over backwards.
Yes.
So in theory it just goes straight on in that angle.
So we can adjust how far it goes and how high it goes by adjusting how far we stretch the bungee and how high we angle the guides.
Excellent, thank you.
We've got the whole thing at an angle, so yes.
Now you've all been firing hoops virtually from the word go. Is this going to be the finished machine?
I've no idea. It's still being developed.
But what did you decide? It was most important to start experimenting first?
Yes, start experimenting and find out how the various bits behave, how much power there is in a bamboo cane, how much extra we get with the bits of rubber, whether they've got an efficient release, and more now, what sort of angle we've got to have the ramp at to get controlled flight.
And then will you finally sort of build it all together, or are you happy with it like this, do you think?
Oh, keep it honest and nothing.
We'll certainly improve on it if there's time to do so.
Yes.
Yeah.
But your power source is a combination of that which pings like that.
Yeah.
Yes.
any number of strings up until the take-off point.
So you can have more or less added.
When it's built up, yes.
Yes, when it's built up. Otherwise the whole thing falls.
Plus we have a variability on the trigger.
Yes.
By how far we pull the whole thing back.
Good.
So
well,
I think we'll be able to get it across the room, but whether we'll be accurate enough is another problem.
Well, I see you've already got some over the stool at the end there.
That's
by hand,
cheating.
artificially. Cheating, yes.
Ouch.
Let's have a hoop on that and see how...
We now have some idea of the propulsion strategies used by the teams. Basically, they're all using the bungee cord as a major power source. Though life science research have backed up the bungee with the bendable cane, so they really have two stages of velocity. Gordon, do you think this is a good idea?
Yes, I think theirs actually is almost the other way around, in that the cane is the basic propulsion, and they're using a bungee to increase the velocity for the longer ranges.
So this is almost the same philosophy as having a multi-stage rocket.
Exactly, yes, it is. They're all, I think, having problems that we can demonstrate only too well with our little model. Problems of stability in flight. The problem of holding the orientation of the hoop in such an inclination that it catches on the peg rather than spinning round it.
Well, let's go and play with our model. Our model is made of cardboard and is no more, it's merely an illustration of the principles involved and how difficult it really is. We've also got a scaling problem in that by making everything in 8 scale and distance in 8 scale, it doesn't, of course, scale all the other physical forces, does it?
That's right. Linear scaling doesn't give you a satisfactory dynamical similarity, to use the jargon.
Yes. Well, so this won't work. I mean, we already know this.
We shall be very pleased if it does.
But one of the principles we've tried to use in this model is to launch the ring, the hoop in such a way that it should theoretically at least travel in this orientation. Mm-hmm. It doesn't, in fact, for reasons which we'll see at the moment. Let me go and fire this to my best of my ability.
Not bad. Not bad.
Now, what actually happened was, as far as I could see, is that rather than traveling in a nice organized way, which of course what the competitors would like to do, we got some spin.
We took on a spin. I'm not convinced it was a forward spin that you're showing, actually. I think it might well have been a rearward spin.
Well, what would we
which is worse, of course, than either a forward or no spin.
Yes, because a rearward spin, of course, is the worst of all cases, that you hit the back, the leading edge first, but then you fall off, yes, rather than maximizing your chance.
Exactly.
Well, Gordon, I wonder if the teams will do better than we've done. I think we would hope so. Let's go and have a look at them later on.
How about a piece of something through there, which is anchored here by a G-clamp?
That is starting not to look strong enough, actually.
Yeah, we'll put another piece across the back.
We must put a bracing on that of some kind, if only it's just another bit of 2x1 on the outside. I hope this doesn't contravene anybody's arms limitation treaties.
It's moving all the way.
Definitely got the firing rate.
It's come right round again.
Yeah.
See?
Yeah, all right, we've got to block that solid.
It wants to be a little bit higher to give us a little bit more angle as they go forwards.
Sorry!
You didn't mean it.
You did ask for it, let's be fair. Sorry about that.
There's only half an hour to go now, and the hoops are beginning to fly all around the studio.
We've got a nail poking up on the final takeoff point.
You nearly got me just then.
Ah, sorry about that.
You've got the noisiest of all the machines. What makes the big thwack in this?
This chap's striking the end of the board, I suspect.
But isn't that likely to waste an awful lot of energy? Isn't there an awful lot of energy still left in your pusher?
Well, there is indeed, yes, and this is probably one of our basic design flaws. We're expending an awful lot of energy to get very little, I think.
Well, I mean, it's free, as it were. It's
it is indeed, yeah. But it's just as well we built the frame as strong as we did, I think. Otherwise, we'd have had real problems.
How are you off for range now?
I think we've got the range just about. Now the problem comes in calibration.
So you're putting a pointer on?
We are indeed, yes, and we're going to hope to calibrate that in the next few minutes.
So what you will do is you'll both point in a different direction. You change the bearing and the elevation for each of the three pegs.
That's right, yes. That's right.
There's your rangefinder.
Oh, right, excellent.
Well, I see, the scale along the side if you can.
Yeah, that's right.
Fire another one.
Yes, OK. Can you throw me a hoop? OK. No, we haven't fitted the trigger as yet, but we are going to put a trigger there.
Well, not bad. But I'm glad to be at this end rather than the other end.
Quite so.
Thank you very much.
That's quite all right. Right, OK. Beautiful, beautiful. Excellent. Worthy of the National Standards Institute.
You can vary that length.
Yeah. But I don't think we need to go that way, because surely we need to...
Peter, I'm sorry to disturb you. There's not much time left, but just a couple of questions, if I may. I'm interested to see that you're not using any guidance in angle of direction.
Yeah, when we first constructed the thing, we had this thing on at right angles, and we looked to see which direction the hoops were firing off at. Mm-hmm. We found they consistently went that direction, so we just twisted our chute in that direction, and we find that now all of them will go off in that same direction. We don't...
You're just taking what comes, in fact, and the direction's consistent.
Yeah. At one stage, we were thinking of putting some panels along there, so it would be guided in that general direction. But
they're not needed.
We found it's not necessary.
Right, I'd better let you get on with it. Time's nearly up.
OK, thank you.
I'm just going to take that corner off, are we not? Yeah. You got the knife.
Needs to go down enough.
But that was a pretty good. It was a pretty good shot. You've certainly got a long barrel. Are you about to fire another one?
Yes.
What we do a statistical. Yes, they're all.
You're a bit high.
Lower the front down again.
But you're trying to constrain. You're trying to constrain your hoop to fly, roughly speaking, 45 degrees. Are you?
Yes, that's the intention.
The catches the top of the.
But it appears to flatten. It appears to flatten out in flight.
This is the problem at the moment.
We've tried to overcome that by actually opening the mouth up so that it tends to flip upwards. We okay then?
You're firing again.
Yes.
Well,
shall we slide it across about an inch, Ed?
Your trigger mechanism at the moment is you're merely pulling that pin out.
Yes.
Firing pin.
I see. You're using the firing pin in its most literal sense. That's something I like about your machine. It's a relatively long travel which you have on your bungee, which makes for good energy transfer to the hoop.
Should improve the linearity of flight.
And you obviously have no range problems. Well, let's watch this last one. Well, nearly well done. Thank you very much.
Another down a bit, Ed. About an inch again.
Okay.
Yeah.
Time's now up and we're ready for the first test, and on the firing line are ICL.
You ready?
But before they start firing, Heinz, could you explain the scoring system?
A really delightfully simple system. 10 marks for each hoop on the pin of its correct color. Now ICL. I will start my watch as soon as you fire your first shot.
Right. Okay?
Yep.
Short.
More elevation. Hold it. Hold it.
Okay.
Launch. 25 seconds gone.
Right. One more.
Right. Yep.
Change your color.
Right, green, please.
Another 10 seconds to go. That was your last shot, I'm afraid. Time's up. 90 seconds up. Thank you.
Numbers of correct coloured hoops over the pegs are, I'm afraid, none.
So I'm afraid the score is the same.
Thank you.
Well, that was a magnificent score of 0. I wonder if Contron can beat it.
Right, gentlemen, load your machine. You're going for the blue peg first. In your own time.
Too very.
Oh,
Well
yes.
done.
Stop.
Very good rate of fire.
Yes. Ah, bouncing off again. One.
And 3 near misses.
Red, isn't it, next? Right, up 2. Okay.
50 seconds.
Right, lined up.
Well done.
Straight on. Oh,
Ooh.
nearly. Getting so close.
You hurry, you get one more off. Well done.
Hey!
Finish, 90
done.
seconds.
Right, so
Well done.
that's 3 altogether of the right colour on the right pigs.
Scoring 30.
Congratulations.
And the third team to be tested are life science research, and they've of course got 30 to beat. Heinz?
I'll start my watch on your first firing.
Bit of a fluffy one. Oh, lovely. Machine problem.
Yes.
40 seconds.
Adjusting the machine for the next colour.
It's rather idiosyncratic in its behaviour.
When it works, it's very, very good, but... Oh,
That's it.
oh dear.
We'll have to just keep.
Yes?
Well done.
Suddenly.
When it works, it works.
Got time for one more shot.
Oh,
I'm afraid you've got to finish it.
nearly. Very nearly the same, but it's actually 2 over.
Scoring 20.
No wonder Hoopla stores make money. You'll agree, Gordon, this was much more difficult than it looked.
It was more difficult than we thought, or the teams, I think, before they started. But I think it's fair to say that the right machine won. Contron, although they won only narrowly, they had a lot of very near misses. Hilary.
So, in spite of the difficulty, Contron Electrolab won through in the end. Our thanks to them, and also to Life Science Research, and to the gallant losers from ICL. Thanks too to our judges, to Professor Gordon Higginson and, of course, Heinz Wolf. And we'll be back again next week with another difficult problem and 3 new teams. Until then, goodbye.